to where we need to be. So we're at the line past the called print bar. So we're going to pop N off the stack. We're going to increment J, add 1 to it, store it, and then we take and go back up to the top of our 40 and continue on. Okay? Make sense? All right. All right, so I'm not going to bore you by going through the other two. Again, it's going to go through and do the exact same thing for 13 and 17. It's going to do the exact, again, it's just going to do the exact same thing. So that's that. All right, so we talked a little, so basically what we saw with the passing, in this case, of how many stars we want to take, that was call by value. And again, it's using stack relative to get that off of the stack and put into that local variable. Goof something, or is this just in here twice? Oh, all right. This is the same program, but the thing that's different about it is the 3 global variables that we had before. We've now made them local variables within main. So, real quick, let's just look at this. I'm not going to run the whole thing. Come in here and do 23, so I'm going to copy this over. I'm going to take and clear my memory. Compile it, and then I'm going to start running it. All right, so right off the bat, we notice no memory has been allocated because we don't have any global variables, so it doesn't happen. So we're going to jump down to main. And now we're going to take and we're going to allocate spots for number of points and for value and for J. So because these are local variables, they get allocated and they're actually put onto the stack. Global variables are out there that are actually in regular memory. With this, again, they get allocated locally. So we take and we input the number of points. That goes in the number of points. And then we start the for loop. We do the comparison. We have the condition for ending the loop. So now we get the input value, and it goes into directly onto the stack. Again, using stack relative. We'll go back here. Back here for a second. So if we look at the previous assembler code, and this is on page 49 in the handout. So I've got the exact same statements here. So I've got a deci for input a decimal. I have the same variable name, but my addressing mode is different. So, and what we're looking at right now is using stack relative addressing, where before it was using direct addressing. So where the variable is actually declared, that's going to determine where its memory location is, whether it's in memory or whether it's actually on the stack. So again, everything else is the same. So we're going to take and we're going to push the value out onto the stack. We're going to call print bar, which takes and pushes the address, the return address out there. In this case, it's 46. And then this. The subroutine works exactly the same. If you look at the code, it's exactly the same. So we have the same addressing modes as we did before. So let me just go through this screen. Okay, now we have our break. So we've now printed the 3 stars. We do the carriage return, and now we're going to do the return. Again, it's return 2, so we have an offset on the stack as to where the return address is. Again, in this case, it's the second. It's basically 2 bytes in. Down the stack. So we do the return, and it pops off the K, which was a local variable, return address, and it jumps us down. And then again, M is going to get popped off of the stack, deallocates memory, and we carry on with the rest of the program. So we run the whole thing, and again, you can see the output with all of the bars, and it even handled the 0 correctly, so there's a nice blank line there. Okay? So same program. Addressing mode is different, again, because of where the variables actually get defined. So we did that. Okay, so we're on to page 56 of the PDF. So the previous 2 examples, the function that we call the print bar didn't return a value. So it was a null function. Well, now what we want to do is we want to take and we want to look at what happens if we have a function that is going to take and return a value. So really, the only thing that's different about this is we're going to take and we're going to have storage on the stack for the return value. So that's the thing that is different. So we're going to push the storage for the return value, and like before, we're going to push the actual parameters, push the return address. We're going to make the call, and then any local variables that we have are going to get pushed out onto the stack. They're going to be initiated when we start that. So here is our old friend, the bin coefficient little program here. So if we look at main, we're going to be calling the function, and we are going to pass it 3 and 1. And we have that call actually in the cout, which is, it's legitimate. You can do this. So we do a cout. We have a little tag here, bin coef 3, 1 equals, and then we have the call, and we're going to pass the functions. We're going to pass the parameters down. So again, coming over to our simulator, I'm going to take and look at figure 625, and clear my memory. Okay, so everything is fine. Go ahead and assemble it, and now let's step through it. All right, so again, Gaza.
Why does it always allocate space and move up and down the stack by 2?
Well, actually, it's going to depend on the size of whatever gets pushed out onto the stack.
Okay, I get it.
So, integers, we've been using integers. And an integer is always 2 bytes. So, the memory address, a memory address holds a byte. So since an integer is going to take up 2, the address for the next thing down the stack that address is going to be basically 2 bytes later. If we had if we were dealing with characters, all right, and I forget, I think a character I think that also a character is stored in 2 bytes. I'm not sure, but anyhow, if we were trying to store 10 characters, characters probably not a good example. Let's take float, okay? Depending upon, float is, take it to hold a float, you're going to need a lot more bytes. And I'm not sure if we have an example of this. But however long that is, and let's say, the float takes up 8 bytes. To get to the next variable down, if we're doing stack relative, okay, the offset is actually going to be 8. Because the stack pointer is always at the top, and that offset is actually the number of bytes that you have to go to get to that next variable down in the stack. Okay? Make sense?
Yep. And the debugging signs, like #2D, that's telling you that it's taking up 2.
Yeah. All right, so we don't have the global variable. So again, Memory, we've got nothing that has been allocated out in memory. So we drop down here. And first thing that we're going to do is, okay, good. So the first thing that we're going to do is we're going to do a string out. So now we have the label of what we're going to do. We're going to take and load 3 into the accumulator. We're going to store that out on the stack. We're going to put 1 in the accumulator, store that out on the stack. Okay. Now, the next thing that's going to be done is space on the stack is going to be allocated for the return value, the return address, and any parameters. I'm sorry, I haven't done it yet. So next thing we're going to do is we're going to push space out on the stack for the return value, which in this case is going to be an integer, and then also for the local parameters within the function. So we do that. So again, if you look, return value is 0, n is 3, k is 1. That's out on the stack. Now we take and we call our function. So when we do that, the return address is pushed out onto the stack, and then we're in the function. So we have 2 local variables, y1 and y2. Space for those gets allocated. Then we start, the first thing we have is an if statement. If k is 0 or n is equal to k, so the 2 parameters are the same, we're going to take and we're going to branch. So the first thing we're going to do is we're going to check is k 0. So we're going to take and we're going to load k into the accumulator, and then we're going to do a break on quality. So break on equal. So since we're we want to do a comparison to see if it's 0, we don't have to do a compare or do anything to the accumulator. We're just evaluating what's in the accumulator. So it's not 0, so we get that break doesn't happen. We load n into the accumulator. We compare it to k. So again, CP just sets the status flags, doesn't touch the accumulator. So we're going to break on less than. Well, it's not less than because we don't have a negative number. Well, actually, okay, yeah. We're going to break if it's less than. So this branch, not break. Just say break. We're going to branch. So since they're not equal to each other, we're going to pop down to the else. So this is where we're going to take and make 2 calls to bin coefficient and get the y1 and the y2. So firstly is a call with n minus 1 in k. So load into the accumulator, subtract the 1, store that out on the stack, load k, store k, push space for the return value and for n and k, push that out onto the stack. So if you notice, that's now out on the stack, and we do call to bin coefficient. And that address gets pushed out onto the stack. So then we just take and, bin coefficient is going to do the exact same thing once again. And we don't have k equal to 0 or n equal to k. So it's going to take and do two calls to bin coefficient. So it sets it up exactly the same way. It pushes another instance of return value in NK out onto the stack. So here we have space for the return value. We subtracted 1 from n. So now we have 1 for n and 1 for k. And we take and we're going to call bin coefficient again. And once again, notice the address has been taken and pushed out there, return address. So on this iteration, we come through, we look, is k equal to 0? It is not, so we're going to see, does n equal k? Load n, compare it to k. And if you notice, when we do that now for this iteration, the z status for this has been set to 1, which means if your z status is equal to 1, it indicates a 0. Correct. So, branch less than, it's not less than. So now we're going to take and do the return 1. So we're going to return 1. So we load 1 into the accumulator. We're going to store that in the return value using stack relative addressing. So once we do that, notice that the value for return value is 1. So now I'm going to do my return. So this is going to take and pop y2 and y1 off and get that return value, and that goes into the to the program counter for our next step. So y2, y1, and return address, they've been popped off. So we return, we want to take and we want to get the values for k and n and the return value. We pop those off of the stack. So now what we want to do is we want to take and store that return value and put that into y1. So we load it. We store it, and y1 now is equal to 1. So now we've got a value for y1. Now we have to calculate for y2. So we set this up. So we're going to take and we're going to push two parameters, n minus 1 and k minus 1. Now, if I look at here, I actually have 2 k's and 2 n's sitting out on the stack. So how does the assembler know which one of these to actually go out and grab.
If you do stack address, it's going to take the next one on the stack.
So basically the offset is being kept track of, in this case, for each call that we do to our function. So this is taking and saying, load n into the accumulator. So the n that we're actually going to load in is at memory location FBDF. So we load that in, we subtract it, we push that out onto the stack, we load K, subtract 1, push that out onto the stack. The memory then gets allocated. Now, if you notice, if you look at the stack right now, can you guys see that? Should I blow that up? Okay. So now that we've actually pushed return value in n and k out onto the stack. If we look, if you remember the first time that we went through this, return value was actually equal to 0. And if we look further down the stack, we can see that yes, indeed, that return value is equal to 0. In this case, it's 1. Anybody want to venture a guess as to why that happened? Why do we have a 1 and not a 0? Where'd the 1 come from? David, you're quiet. Where do you think the 1 came from? Oh, come on, use that brain. Anybody want to guess?
Can you explain the question again?
Well, if you remember when we did the call for Y1, when we were setting up that, when we pushed, in that case, return value n and k out there, return value was a 1, it was a 0. Now it's a 1. And I was just wondering if anybody knew why there was a 1 there and not a 0.
Because we stored it there when we passed the if statement.
Right. What happened here is we are basically reusing memory that was already out there. So, before this, we popped everything off. We deallocated F, BB1, B3, and B5. Well, now we're going to need to push the 3 variables back out onto the stack.